Hi, this video is about Coulomb's law. Coulomb's law involves electric force, specifically electrostatic force. When electric charges are still and not moving, what is the force between two charged objects? So I've got two balloons here, one negatively charged and one positively charged. We know that they're going to have a force of attraction, and this force is equal and opposite. They both experience a force, and they both are equal. Now, this is a little bit more simplified than reality because in a balloon like this, really each of these charges are attracted to each of the other charges. And so we have a bunch of little microscopic forces that are all acting here, and they're acting in different directions. But we're going to keep it simple. And in order to do that, what we do in physics is we take situations that are complicated like this and we simplify them down to a point. And so we'll take this balloon and we will simplify it to a single point. And likewise, we'll take this balloon and simplify it to a single point as well. And these are called point charges. And I think you can see why. So one of them is negative, one of them is positive. And we also will have an amount for the charge as well. But for now, we'll just say negative and positive here. So the force between these two charges depends on how much negative charge there is and how much positive charge there is. Or if they're both positive, how much charge total you have. And the way that we denote charge in physics is with the letter Q. So this would be Q1 and Q2, the amount of charge that's present here. And then we also want to know what is the distance between these two charges. So the separation distance between charge 1 and charge 2, we just use the letter D. Sometimes people use R, but this is the distance between the two charges. So the electrostatic force is going to depend on the product of the charges, Q1 times Q2, and it's related to the distance by the inverse square law. So as you increase the distance, the force has to spread out to cover more and more area, and so therefore it follows the inverse square law. Now, whenever you do this, I don't have an equal sign here because force is always measured in newtons. But these units over here are not newtons. They are coulombs times coulombs divided by meters squared. That doesn't have anywhere close to newtons. So what we need is some kind of conversion factor that we can put in here so that these two equal each other. And that conversion factor is going to have units that cancel out the coulombs and the meters squared. So it's going to be coulombs squared on the bottom, meters squared on the top. So those will cancel, and we need newtons in here as well. That'll give us units of newton. So what is this conversion factor? How much is it? This conversion factor is 8.99 times 10 to the 9 newtons times meters squared over coulombs squared. And this conversion factor we represent with the lowercase k. And this is the constant that we're dealing with here. Okay, so now that we have this k value, we can go back to this equation up here and make it an actual equation by putting k in front, k, and say that this is the electrostatic force. So this is Coulomb's law up here. So I'm going to erase all this other stuff and get it out of the way because I wanted to show you a comparison between this law and another law, and that is the gravitational force. So the gravitational force between any two objects in space is the mass 1 times mass 2 over distance squared. Now, if you look at these two equations, they're very similar. They have the same, kind of layout, and both of them have a different conversion factor. And so the conversion factor for the universal gravitation equation is 6.67 times 10 to the negative 11, and that's newtons times meters squared over kilograms squared. Whereas the conversion factor here is 8.99 times 10 to the 9 newtons times, we have meter squared over coulomb squared. So that's a big difference, because this is times 10 to the negative 11, this is times 10 to the 9. That's, nearly 20 orders of magnitude, which is, a trillion, like it's a big number of difference between them. This one is much higher, and so the electrostatic force is much stronger than the gravitational force. And the way that this makes sense is, the gravitational force really only acts if one of the masses is really giant. Gravitational force doesn't act between ordinary objects. The electrostatic force acts between ordinary objects all the time. In fact, it's what holds atoms and molecules together. It's an extremely important force. So that's all I've got for you in this video. Remember, shortcuts make long delays.